Hello, everyone. Let's get started here. Jordan. I've got my winter hat on. I went for a walk earlier and it was like 53 degrees out and it's so cold, and it's amazing how 53 degrees on the fall side feels so cold, but then 53 degrees on the spring side, you're like in a bikini. You're like, woo, it's so warm out. So, but yeah, the weather's been beautiful. It's been awesome. So I definitely recommend getting out there when you can. So your first test opened up yesterday, still open. So if you're like, oh no, I haven't taken the test, take it today before midnight so that you can get credit for that. You don't want to miss the first test. First test is probably the easiest of the semester, so definitely rack in those points if you can. We're moving into chapter 4. So we're kind of going to step away from math for a little bit. I do want you to get a periodic chart. So find one. I had one here, just lying around. Your lab manual has one on the inside cover. Okay, so you can use that one, or your textbook, or maybe you've printed one out or ordered one online. One of my students in the other class, she ordered a periodic chart online. It was like a laminated one, and she thought it was going to be like this big, and she got it and it's like this big. It's so tiny. So she's always looking at her periodic chart like that. I'm like, Brittany, what is that? She's like, it's my periodic chart. It's so little. So I'd recommend something a little bigger and something you're going to feel comfortable drawing or writing on so you can take notes. Okay. A couple more people coming in. Sharing screen here. We're going to open up slides for 4. Atom and elements. Close you up. Okay, so this is just talking about how a farmer needs to know things about chemical testing in order to apply fertilizers and pesticides and herbicides. I mean, chemistry is everywhere. It's all over the place. So elements and symbols. So we'll talk about the simplest sort of base unit of matter, which is the atom or the element. So elements are pure substance. I have a question related to chapter 3 homework. Could I meet with you after class? Colleen, yeah, for sure. Just stay around after class and we'll chat about it. So elements are a type of pure substance in which all other things are built on. So just like letters create words and words create sentences, right? The letters being sort of the base of our language, elements are the base of our chemical understanding. They can't be broken down into simpler substances, and that they can't be broken down into simpler identifiable substances. So we could take an atom and break it into protons and neutrons and electrons. Those are the building blocks of our atoms, but they're not identifiable. Protons are consistent throughout all the different types of elements. So all of the elements are going to be listed on a periodic chart. So given the name of an element, you want to be able to write the correct symbol, and from the symbol be able to write a name. Let's see what the periodic chart has. Okay, so your periodic chart on the cover of your lab manual doesn't have the names. So you may at some point want to invest in a periodic chart that does have the names included on it. sometimes the names and the symbols don't correlate, right? Like potassium is K. I know these, and people who've done a lot of chemistry can probably work around a periodic chart that doesn't have the names on it, but you may want to find one that has the names as well. So here are some elements with their corresponding names. We've got uranium, symbol U for the planet Uranus. Great. Titanium, Ti for the Titans. Chlorine, symbol is Cl, not Ch. Okay. Root is chloros, which is greenish yellow because the gas, chlorine gas itself, has this kind of icky yellowish color. Iodine is I. Iodis, which is violet, because iodine in its gaseous form has this really pretty purple color. So, you know, I mean, we don't need to go through all of them, and I don't expect you to, you know, have their source name memorized, but you do need to be able to go between these. So throughout the semester, I'm going to say, hey, magnesium oxide, and you're going to be writing the symbol for magnesium pretty quickly. So as far as your chemical symbols are concerned, chemical symbols represent the name of the element. They usually consist of 1 to 2 letters and start with a capital. On the left here, we've got 1-letter symbols. So carbon is C, nitrogen N, fluorine F, oxygen O. And then to the right, we've got a couple examples of some 2-letter symbols. Cobalt, CO, calcium, Ca, aluminum, magnesium. Hannah, on our lab due on the 4th, it asked for the luster of an element. Are we going to go over that? Yeah, we'll be going over luster, but luster, you'll probably just end up looking that up online because you won't have the actual samples in hand. So all these correlate. These are easy, they make sense. So here are some common elements. Great. Some of them don't make quite as much sense. So let's see. Copper is not CO, it's Cu because it was called cuprum. Iron, which its root is ferrum, is Fe. Potassium, which is root is kalium, K. Silver is Ag. Okay, so expect to see some of them with similar symbol names and some of them are sort of different. So here we've got silver is Ag for argentum. Au is our symbol for gold. That's why you might want to have one with the names on it. Okay, so real easy. Go ahead and write down the symbol for each of these. More so just getting you practiced with looking at the periodic chart. Okay, so nothing too complicated here, just trying to get comfortable with the periodic chart. So iodine, which is all the way over to the lower right-hand corner, number 53, its symbol is just going to be I. Iron, which is number 26, sort of somewhere in the middle, that's going to be Fe. Magnesium, which is number 12 over to the left, that's going to be Mg. Zinc, which is sort of 2/3 of the way over, number 30, that's Zn. And then nitrogen, number 7, up at the top over on the right, is going to be just N. All right, so nothing too complicated. All right, so this, yeah, there we go. Okay, so this one, I want you to find the names for these. P, A, L, M, N, H, and K. Okay, so A is P, which is phosphorus. BAl, that's number 13, that's aluminum. CMN is number 25, that's manganese. That one gets confused a lot with Mg, which is magnesium, right? They both have M's and G's and N's. So just make sure that you're keeping those separate from each other. DH is hydrogen, number 1, and EK is potassium. So again, yeah, manganese, not magnesium for that one. So here is carbon. We're looking specifically at carbon, and carbon has the symbol C. The cool thing about carbon in a lot of different materials is that depending on how you arrange them, you can get totally different properties and materials. So graphite, the tip of your pencil, is made out of carbon. And it's actually made out of these little hexagonal rings that sort of are lined up as sheets. So when you write, the sheets come off onto the paper, and that's what you write with. Diamond, on the other hand, has a framework structure. So the carbon is structured a little bit differently. Instead of it being sort of in these sheets, it's in a 3-dimensional lattice structure, which is really, really strong. So you get the properties of diamond. You can make it or form it into nanotubes. And I don't know what this is. Buckminster fullerene. I don't know what that is, okay? So if someone wants to look it up, you could tell me what it is, but I don't know what it is. Probably does something really, really cool. But nanotubes, carbon nanotubes are really interesting. Okay, so over here, we've got an entire little swimming pool of mercury, right? Mercury is a silvery, shiny element. It's really the only metal that is liquid at room temperature. This is not something you would want to swim in. Mercury is very, very toxic. There's actually a couple different ways that you can accidentally ingest mercury. You can inhale it. You can absorb it through contact with your skin, and you can also ingest it in foods. So if you hear of mercury poisoning, or when you're pregnant, don't eat too much fish. It's because you can get a bioaccumulation of mercury. If you've ever heard of the Mad Hatters, they pretty much had mercury poisoning. So when they would paint on the hats and work on the hats, they would paint and use mercury, and they would lick the brush and write in it, and it would drive them crazy. So just don't consume mercury. So why does it not work so well? So in the long term, mercury destroys certain types of proteins that will then disrupt cell function. So it can cause brain and kidney failure, but really that brain failure, mental retardation, and decrease in physical movement. So you can test it though. Really, it's not something you have to worry about. We don't have a whole lot of mercury in the environment. There are certain areas where it can be bioaccumulated again, like certain type of fish and things like that, but shouldn't have too much of a problem. Okay, so this thing is always just in my way. The periodic table. So here is a picture of the periodic table. This one is a very, very simplified periodic table. You'll see it doesn't even have the atomic mass, and it doesn't have the name on it. But we can look at this. So the periodic table is an organizational chart of 118 elements. They are grouped based off of their properties. So we put them in similar order that have similar properties, or similar places when they have similar properties. And they are ordered in increasing order of atomic mass and atomic number. So atomic number here, we've got 1, and we'll talk about it a little bit more, but that means how many protons it has. So 1, 2, we read it like a book. So when we get to the end of the line, we come over 3, 4, 5, 6, 7, 8, 9, 10, come over 11, 12, 13, 14, all the way to 18, 19, and then we get into here where the transition metals are. So when looking at your periodic chart, depending on which one you have, the one on the inside cover does have the line. So you'll see this sort of bolded line. You may want to highlight it, but definitely identify that on your periodic chart. That separates metals from non-metals, okay? So when looking at this periodic chart, and this line, you can kind of like extend it to underneath hydrogen, because hydrogen is obviously not a metal. It has some qualities like these, but it's definitely a non-metal. So all these blue things, including the lanthanides, and if you're wondering, you've always had this little truncated thing on the bottom, where does that go? Well, do you see how the periodic chart goes from 57 here to 72? We're not just missing all of those elements with those number of protons. They're right here. Here's 58 all the way through 71, and then there's 72. So that gets pulled out. This is known as the F block as well. Why isn't it inserted in there? Because this is just more convenient to get onto a piece of paper. Okay, otherwise we would extend this out, and there would be another stair step at that point. So we've got all of our metals. You got your zigzag line. We've got our non-metals, which are the yellow. And then we've got these specific ones along here. So pretty much all of them on the zigzag line, except for radon and aluminum. Those are known as metalloids. And metalloids have properties of metals and properties of non-metals. Sometimes they're called semiconductors. They're really useful in electronics. So we, for instance, we don't call Silicon Valley Copper Valley. We call it Silicon Valley because silicon has such a useful quality. We can turn circuits on and off using things like this. So let's talk about groups and periods. So groups are the things that go up and down. Think of the groups as your columns, your vertical columns. Periods are the horizontal rows. So elements are arranged according to similar properties. We have, looking here, we've got what are known as the main group elements. And then we've got the transition elements. This calls it the representative elements. You can call them main group elements as well. So these 2 over here and these 6 over here. These are the main group. They have predictable properties to them. So we kind of like them. In the middle here, and this middle also includes the lanthanides down here. These are known as transition elements. They are much more varied in their, specifically in the charge that they can produce. So these have predictable charges. These guys have unpredictable charges. And we'll talk about charges in a little bit. There are names for a lot of the groups. So the first group here, these are the alkali metals. So everything in group, this is called group 1. You'll hear me say column 1, group 1. I'm talking about this here. This is the alkali metals. Group 2 or column 2 is known as the alkaline earth metals. If we jump over to, this is group 3. Okay, so when I say, hey, go to group 3, I'm not talking about this. I'm talking about this over here. These are the main groups. These get specific numbers. Yes, these do get numbered sometimes as B1, B2, B3. It depends on the chart that you're working with. But when I'm talking about column 3, I'm talking about this here, okay? So this would be 1, 2, 3, 4, 5, 6, 7, and 8. Group 7 are the halogens. That includes fluorine, chlorine, bromine, and iodine. And group 8, all the way at the end, those are known as the noble gases. Helium, neon, argon, krypton, xenon, and radon. So now we can sort of start to look at the periodic chart and see, okay, there's a lot of metals. Most of the metals are to the left of the zigzag. The non-metals are to the right of the zigzag. I've got 2 groups on the left and 6 groups on the right that have names and predictable charges. Then I've got this stuff in the middle that's a little bit sloppier. So for as far as group numbers are concerned, we have using the letter A for representative elements, or for the main group, we have group A1 through A8. You're going to hear me just call it group 1, 2, 3, 4, 5, 6, 7, 8. This specific text calls the transition metals group 3B through 12B. You're not going to hear me really use that a whole lot. I'm going to be doing mostly this here. So every element has a group, and then it also has a period. So if your periodic chart doesn't have numbers, the one on the inside cover of the lab manual does. Mine here, which is from 151, doesn't have one. But periods are the horizontals. So next to hydrogen, you could put a 1. Next to lithium, put a 2. Sodium gets a 3, potassium gets a 4, rubidium 5, 6, and then fat Frankie in the lower left-hand corner will get an 8. Where am I? Miss it. 1, 2, 3, 4, 5, 6, 7. I got carried away. 1 for hydrogen, 2 for lithium, 3 for sodium, 4 for potassium, 5 for rubidium, 6 for cesium, and 7 for fat Frankie in the lower left-hand corner. So looking at group 2, all these guys here would be included in group 2. Looking at period 4, everything here would be in period 4. Calcium, we could say, is at position group 2 / period 4. So we've got the alkali metals, we've got the alkaline earth metals, transition metals. No common names. They do have common names, but like we've got the chalcogens, but we're not going to use that. But you do need to know or want to know the halogens and the noble gases, alkali metals and alkaline earth metals. Again, these guys with the pretty colors, those have much more predictable properties than these guys in the middle. So here is group one. Group one called the alkali metals. So everything in group one has a relatively, they have similar properties. They do similar things. They all tend to be a metal and they tend to be highly reactive. So we've got lithium, sodium, and potassium. They all kind of even like look the same. They're all very reactive. Halogens on the right side, we've got chlorine, bromine, iodine. These guys, again, will all have relatively predictable charges and properties. So I want you to pick out the right one here. So it says, identify the element described by each of the following. It's in group 7A and period 4. Group 2A and period 3, and group 5A and period 2. So again, just getting comfortable with your periodic chart. So figure out which group you're going to, which is your column, and then move down from there. All right, so number 1 is group 7, period 4. So group 7 is the column where fluorine is, our halogens. Now we want to go to period 4, but fluorine is not in period 1. Fluorine is starting in period 2, okay? So fluorine will be 2, chlorine will be 3, bromine will be 4. So A, bromine. Number 2A, period 3. Okay, so we go over to 2, which is my alkaline earth metals. And I've got to go down 3. We're at beryllium, but beryllium is really at 2, 3. So we go 1 down, magnesium. Group 5A, 1, 2, 3, 4, 5. So 5 would be my nitrogen column. Period 2 means nitrogen. We posit nitrogen. So we've already talked about this, but the heavy zigzag line separates our metals from our nonmetals. And then we've got the metalloids that are located along your zigzag line. There are metalloids, everything along the zigzag line, but aluminum. Aluminum is not a metalloid. Aluminum is definitely a metal. So a couple things about metals. Metals are shiny and ductile. They're good conductors of heat and electricity. And another thing I want you to put down next to metal in your notes or somewhere is that they like to form cations, okay, which is a positive charge. And we'll get back into that a little later. Nonmetals are dull, brittle, and poor conductors of electricity. They're good insulators though. So we use those things for insulation. We don't use them to conduct things. These tend to form anions. Anions form a negative charge. So an example of each of these, an example for this one, magnesium, Mg, it likes to form a 2+ charge, always. Non-metal, let's do oxygen. Oxygen likes to form a 2- charge, okay? So that thing in the upper right-hand corner, and again, we'll come back around to this, but positive charge versus a negative charge. Then we have our metalloids. They're better conductors than non-metals, but not as good as metals. But you can use them as semiconductors and insulators, and it's really useful that you can sort of flip on and flip off their conductibility, so you can use it on a circuit board. All right, so here is a metal, silver, here's a metalloid, and here's a non-metal, and just some of their properties. So go ahead and identify these guys. I want you to identify them as a metal, a non-metal, or a metalloid. This ability to identify seems to slip people's mind. It's so simple that they forget how to do it. So there's the zigzag line. So identify each of these as either a metal or a non-metal, because that's going to follow us throughout the semester, because how we name things with metals is different than how we name things with non-metals and such. Okay. Identify each of the following elements as metal, non-metal, or metalloid. So A, sodium, that is definitely a metal, number 11. It's way over on the left side of the periodic chart. B, B, chlorine, which is number 17 under the halogens. That is a non-metal. C, silicon, number 14, that's a metalloid. D, iron, I mean, I don't even really need to look at it. I know iron's a metal, but it's number 26. It's in the transition metal area. We're going to call that a metal. And then carbon, C, definitely not a metal, number 6. So metal, non-metal, metalloid, metal, non-metal. Does anybody have any questions on identifying those three? If you do, just unmute yourself and you can ask me. Because I want to make sure we can do that. I want that to feel really, really simple. Obviously, if you didn't have a periodic chart, it wouldn't be so simple, but you will have your periodic chart with you on your exam. So hopefully that feels pretty easy. Okay, great. So select all the metals, select all the elements that match each description. Metals in group 4A. Okay, so if we go to 4A, so that would be hydrogen, beryllium, boron, carbon. And so if we look at carbon's row, the metals are going to be tin and lead. SN and PB are going to be the only ones. Non-metals in group 5A. So 5A is the nitrogen group. Non-metals there are going to be nitrogen and phosphorus. AS is a metalloid. And then the other ones, metalloids are metals. And then C, what is the metalloids in 4A? So 4A is again the carbon group. That's going to be Si and Ge. So of all the elements that we see on the periodic chart, 20 of them are essential for the well-being and survival of the human body. So there are 4 elements that make up 96% of our body mass, which is carbon, hydrogen, oxygen, and nitrogen. We are going to spend a lot of time on carbon, hydrogen, oxygen later on in the semester when we get into the organic chemistry. When you find materials that have carbon in them or carbon hydrogen in them, you're dealing with hydrocarbons. That's organic chemistry. There are these things called macro minerals. They are usually, not always metals, but a lot of times they're metals. I guess we've got chlorine and sulfur that aren't. But there are other elements that are involved in the formation of different things in our bodies. So calcium, phosphorus, potassium, chlorine, sulfur, sodium, magnesium. So, you know, if your salt levels are low, if you don't have enough sodium in your system and enough calcium in your system, it can have an effect on your blood. It can have an effect on your bones, your teeth. If your magnesium levels aren't high enough, you can start to get muscle constriction and contractions, right? So your muscles will start to tighten up. So they'll say, you know, eat something with magnesium or eat something with potassium in it, like a banana. So we need all these vitamins in order to keep our body moving properly. So here are all of the elements. The main elements for our body are hydrogen, copper, nitrogen, and oxygen. And then there are these macronutrients. So these blue over here and these blue here, these things we need in relatively high abundances. And then we have some elements that help to fine tune the body, or our micronutrients. So we don't want a whole lot of cobalt in our system, but we need a little bit of it in order to help the body function. Okay, so the smallest identifiable particle of matter is going to be the atom. An atom is the smallest particle of an element that retains the characteristics of the element. So if I have a big hunk of aluminum, and I was to take that aluminum and cut it in half, and cut it in half, and cut it in half, and keep cutting that piece down, the smallest thing that I could get to and still classify it as aluminum, or that it would still have the properties of aluminum, would be the atom. So Dalton's atomic theory, in Dalton's atomic theory of atoms, he postulates that atoms, this is an older theory, okay? So this is from like the 1800s. The theory of the atom, or the atomos, traces back to like the Greeks in BC. But the first sort of real scientific kind of questioning understanding of the atom happened in the 1800s with Dalton. And so he theorized that atoms are tiny particles of matter, right? And of an element, or atoms of an element, are similar to each other and different from those of other elements. So all the atoms, all the carbon atoms in the world are very similar to each other. They have very similar properties. A carbon and a phosphorus atom are not similar to each other. That's why they make up two different elements. Atoms of two or more different types of elements can combine or bond together to form something called a compound. So an element would be sodium, another element would be chlorine, a compound would be sodium chloride. Those two bonded together, which is table salt. And these atoms can be rearranged and moved around to form new combinations during what's called a chemical reaction. So if we are undergoing a chemical reaction, we're just going to move or rearrange the atoms. We're not going to destroy atoms or create atoms. We're just going to move them around. That is going to change a little bit when we get into nuclear chemistry. So my people who've taken 092 or high school chemistry, where you've not really talked about how atoms can transmutate, the atoms can actually change into other atoms, or they can just disappear fully and turn into energy as well. But for the sake of a chemical reaction, we just rearrange them. Okay, so within an atom, we have smaller particles. They're not identifiable though, in that the protons from carbon are the exact same protons as from neon. You wouldn't be able to tell a difference. So what makes a proton? Well, a proton has mass and it has a positive charge, proton. Electrons have very, very teeny tiny mass, but they pack a big punch. They have a negative charge. Neutrons have mass similar to protons, but they are neutral in charge, hence the name neutron. Like charges repel each other, and unlike charges attract each other. So a positive and a negative like to move towards each other. Two negatives like to stay away from each other, which is what electrons do. In the electron cloud around the atom, they spread out. Two positive things also like to repel each other. So my smarties may be thinking, well, then how can you pack more than one proton into a nucleus? If you have 2 protons or 6 protons or 25 protons, if they're all positive, don't they want to get away from each other? They do. And that's a very simple question with an extremely complicated answer. And you would have to take some higher level physics to be able to answer that question, or even try and understand the theories that they have out there they don't actually know. So how these particles were discovered, the protons and the neutrons sit in the nucleus, and we'll go over that, but they weren't the first thing discovered. The first thing to be discovered actually was the electron. So this guy, J.J. Thomson, did this cathode ray experiment. And so he had a cathode ray that contained negatively charged particles, and the particles, which he now calls electrons, had a much smaller mass than the atom. So he came up with this idea that, okay, an atom is not just a solid ball of matter. It's made up of tinier things, and one of those things is what I'm going to call an electron. And he says, and the electron has a negative charge and it has very little mass. Much smaller than the atom. Okay. So he came up with this thing called the plum pudding model, which is where he has a ball and he's got electrons floating around, but the overall atom has a 0 charge. So the cloud that these electrons are sitting in is a positive cloud, like a dust cloud of positiveness. Okay, he didn't really know how to explain the neutrality, so that's what he said. So the plum pudding, I guess these are the electrons are acting as little plums submerged in a pudding matrix. Okay, so there it is. We've got our little negative plums, and then we've got our positive pudding. And the negative and the positive counteract each other so that the whole atom has a neutral charge, which is what we see in nature. So then this next guy came along, Rutherford, and he ran what's called a gold foil experiment, or the gold foil experiment. And he had a really thin piece of gold that was just like an atom or 2 thick. And he decided to shoot alpha particles at it, alpha particles being really high energy particles. And what he found that, and what he believed was that looking at a model like this, because the alpha particles were super, super teeny tiny, and these things were super teeny tiny, that the alpha particles should just go whoop, straight through. Okay. And what he found was that a lot of them went straight through, but every now and then one of them deflected back. And he was like, that doesn't make sense with this idea of the plum pudding model. So why are we having this deflection? So what he ended up concluding was that something had to be in the way, or that there was this very small but very dense, positively charged nucleus in the center of the atom, and that is what is deflecting the alpha particles. So instead of it being just electrons floating in a soup, it is now, there's a center, kind of think of it like a solar system. The center nucleus would be like the sun, and the electrons are sort of orbiting around it like planets. So here's his experiment. He took alpha particles from some sort of radioactive lead. He shot it, and then this round thing is just receiving paper or fluorescent screen, so it lights up when an alpha particle hits it. He saw some of them went through, but other ones were deflecting back, or they were moving through, and then some of them were actually ping-ponging right into that nucleus and deflecting back. So That led to the nuclear theory of the atom, where an atom consists of a nucleus. The nucleus contains all of the protons and all of the neutrons and like most of the mass, like pretty much all of the mass. We don't really consider the electrons are like 2,000 times smaller, so we don't really consider their mass at all. So here we have our, what Dalton thought was this sort of indestructible ball. Well, now we can break up these indestructible balls into a nucleus right in the center. And in that nucleus, there are our protons and our neutrons. And then it's mostly empty space and some really teeny tiny electrons floating around it. So most of this atom is actually a vacuum or empty space. So the AMU, or the atomic mass unit, so one atomic mass unit has a mass equal to 1/12 of the mass of a carbon-12 atom. So carbon-12 being an isotope with 6 protons and 6 neutrons, 1/12 of that would be considered 1 AMU, which is roughly the size of a proton. So a proton has a mass of 1.007 AMUs, a neutron has a mass of 1.008 AMUs, very, very close to each other. We pretty much just say their mass is 1. An electron, on the other hand, has the mass of 0.000549 AMU, so super teeny tiny. Again, like 2,000 times smaller than the protons and neutrons. So when I'm talking about the atomic mass of an atom or how much mass it has, I'm really only talking about the mass of the protons plus the mass of the neutrons. And if you want, you can even write yourself a little equation that says the atomic mass is equal to protons plus neutrons. You don't see electrons in this atomic mass. So some of the subatomic particles, we talked about the proton, which sometimes is written as a P or a P with a little plus. It has a 1+ charge. Its mass is roughly 1 AMU, and its location is the nucleus. A neutron. Neutrons are similar to protons in that they are in the nucleus. Sorry about that. They have the same size, but they don't have a charge. We write neutron as N, or sometimes it's written as N with a little 0, the 0 meaning that it doesn't have a charge. And then there's our little baby electron. Electrons, or E with a little negative sign, they have a 1- charge, but they're super teeny tiny, okay? But even though they're teeny tiny, they're very, very important because of that charge. That charge is what allows us to bond things together into compounds. Where do these electrons live? They live outside of the nucleus. So you do want to know where these particles are and how they relate to each other. So it says, which of the following subatomic particles fits each of the descriptions? So we want to know if it's a proton, neutron, or electron. So A, found outside the nucleus. The only thing found outside the nucleus is going to be the electron. Has a positive charge. Only thing that's positive is our proton. Has a mass, but no charge. So that would be the neutron. Okay, the neutron has some sort of mass, but it doesn't impact our charge in any way. So I talked about mass number. Let's go over that and atomic number. So when you're looking at your periodic chart, you're going to see a whole number, and that's going to be the ordering that it's in. So hydrogen has an atomic number of 1. Helium always has an atomic number of 2. Lithium 3, so on and so on. If we jump, let's go a little bit farther down. Iodine has an atomic number of 53. The atomic number of each element, or the atomic number is the same for each of the atoms of that element, and it tells us how many protons we have. Okay, so atomic number equals protons. So when I'm looking at aluminum, I say, hey, how many protons does aluminum have? It should always have 13 protons. Why? Because its atomic number is 13. That's never going to change. If I change the number of protons, it's not aluminum anymore. So the qualities or the properties are determined by the number of protons. Let's look at another one. Let's say titanium is 22, so it would have 22 protons. Argon has 18 protons, number 18. Cesium, number 55, lower left-hand corner, that has 55 protons. Not too bad. Now, if we're dealing with a charge-neutral atom, which most of the time we are, unless I say it's a cation or something like that, the number of protons should equal the number of electrons. Why? Because the overall atom has a neutral charge. So looking at lithium here, lithium has 1, 2, 3 protons, and it should have 3 electrons floating around it. Carbon over here has 6 protons. It should also have 6 electrons. So if I'm looking at a charge neutral, I want you to find copper on your periodic chart. How many electrons should copper have if it's charge neutral? Copper is in period 4 in the transition middle area, number 29. So it has 29 protons. So if it's charge neutral, it should also have 29 electrons. So there's, this is sodium. There's the atomic number, 11. It's a whole number and it's specific for each element. So if you're dealing with sodium, it will always be 11. It's same for every single atom of sodium. It will be 11. It's equal to the number of protons, and it appears above the symbol. Sometimes, again, depending on the periodic chart, you have sometimes it'll be like over to the left or over to the right. Don't let that throw you off. It's that whole number that's on the upper part of it. So atomic number equals the number of protons. The atomic number of hydrogen is 1. Every hydrogen has 1 proton. If you have 2 protons, you are not hydrogen anymore. You are now helium. You've become something different, okay? Carbon has 6, so it's got to have 6 protons. Copper, 29, got to have 29 protons. And then we kind of already talked about this, but atoms are neutral. So the number of protons needs to equal the number of electrons, because protons have positive charge, electrons have the negative charge. So aluminum, if it has 13 protons, that's going to give me a positive 13. If I have 13 electrons, that's a negative 13. This and this will give me the overall 0, which is what I want. We want the net 0. So silicon on our periodic chart is number 14. It should have Si, should have 14 protons and 14 electrons. All right, so go ahead and fill in this chart here. Figure out the atomic number, the number of protons, and the number of electrons. Hint, it's going to be the same number for all of them. All right, so it shouldn't take too long. So nitrogen is number 7. So we should have 7 protons and 7 electrons. Zinc is number 30, so 30 protons, 30 electrons. Sulfur, 16 protons, 16 electrons. Now, just know these numbers here The electrons can sometimes change. All right. Protons cannot change and still be the same thing. Okay. So I couldn't have, if I had all of a sudden had 6 protons, it would no longer be nitrogen, it'd be carbon. But if I had, let's say I had 10 electrons, I would still be nitrogen. I would just be nitrogen with a charge. And we'll talk about that a little farther. Okay, so the mass number represents the number of particles that are in the nucleus. Because remember, all of the mass is coming from the nucleus. The electrons don't give us mass. So it's equal to the number of protons plus the number of neutrons. The whole number does not appear on the periodic chart. So you will see that there's a decimal number on your periodic chart that I'll refer to as the atomic mass. That's the average atomic mass of all the isotopes. We'll talk about why it's a decimal. But if we're talking about just the mass number of one isotope, it should be a whole number. So looking at hydrogen here, hydrogen has an atomic number of 1. It has a mass number of 1 as well. So how many protons does it have? 1. In this case, how many neutrons does it have? Well, remember that this number here, okay, so this number, our mass number, is equal to my protons plus my neutrons, or this plus this. So if I know this, and I know this, I can take this and subtract it from the mass number to get what's ever left over for the neutrons. So for instance, if this is 14 and 7 of them are occupied by being protons, the other 7 are neutrons. If we go down to gold, we have 197 is my mass number. 79 of them are protons. So I take this minus this, and the remaining 118 would be my neutrons. As your elements get bigger, usually your number of neutrons will start to get bigger than your number of protons. These are not always the same. Okay? And especially when you start to get bigger, you'll start to see that they get a little bit clunkier with neutrons. That's one reason some of those bigger guys can be a little bit radioactive, because those neutrons are just so heavy. It's so heavy in that nucleus, it kind of wants to break apart. So number of protons equals the atomic number. Number of protons plus the number of neutrons equals the mass number. Number of neutrons equals the mass number minus the atomic number. So let's look at this guy here. An atom of lead has a mass number of 207. I want you to tell me how many protons, how many neutrons, and how many electrons there are. I'll give you a minute to figure that out. We've got lead. Find it on the periodic chart. I'll help you out. It's greater than 81 and less than 83. I want to know how many protons, how many neutrons, how many electrons. Okay, so protons for lead, Pb, that is 82. because it's number 82, that's its atomic number. I'm going to skip over neutrons for a second. Electrons, should also be 82 because this thing doesn't have a charge currently. No charge in the upper right-hand corner. That is not a charge. Sorry. So 82 electrons as well. It's equal to the atomic number as well. Now neutrons are going to equal your atomic mass minus your atomic number. Sorry, atomic number. So we're going to take the 207. We're going to subtract the atomic number, which is 82. And we end up with there we go, 125 neutrons. Any questions on how those numbers get calculated? Protons are easy. It's the same as your atomic number. Neutrons, you have to do a little bit of work. And electrons, sometimes you have to do a little bit more work. So I think I'm going to give you guys one more that I want you to tell me. I don't want to start isotopes just yet. Okay, so sulfur has a mass of 32. I want you to tell me the number of protons, number of neutrons, and the number of electrons. Similar question to the last one, just a different material. All right, so if we're dealing with sulfur, my number of protons should always be 16. That's the atomic number. My neutrons are going to be atomic mass minus atomic number. So it's going to be 32 minus the 16, which gives me 16. Sometimes they are the same, okay? Sometimes you will have the same number of protons and neutrons. Sometimes you don't. Electrons, because this isn't charged, we will have 16 electrons as well. So 16, 16, 16. Okay, so we're going to stop there for today because I don't want to get into isotopes just yet. If you have any questions, feel free to stay around. If you don't have any questions, log off quicker than later so that I can know who needs help and who doesn't. Don't forget to take your test, please.